Hello guys, good evening to all of you. Yeah, can you hear me all? Yes, so we were discussing about optical isomerism, right? Last Q&A session, we had discussed optical isomerism, and we have understood that it is the property of a molecule, right, towards plane polarized light, correct? If the plane polarized light rotates in any direction, the molecule is said to be optically active. If there is no rotation, it is optically inactive. Correct? That is what we have discussed. We have also discussed that under what condition the molecule is said to be optically active. What is the condition for that? Condition for a molecule to be optically active? Chirality, right? The molecule must be chiral. No, chiral center is not the property of Kshitish. The condition is the molecule must be chiral. Okay, chiral molecules are those molecules where we do not have any kind of symmetry. Okay, where there is no symmetry, the molecule is said to be chiral, and chiral molecules are optically active. Right? It has been also observed that if the molecule has only one chiral center, it is optically active. But presence or absence of chiral center is not any criteria for a molecule to be optically active. This is what we have discussed. Yes or no? Yes. Have we discussed the representation of molecule? Flying wedge representation we have discussed? Yes, we have also discussed that. Flying wedge and Fisher projection, correct? Okay. We can also interconvert one molecule into other, like flying wedge into Fisher, Fisher into flying wedge. That we can do, but that particular thing we are not going to discuss here, right? Because that is not required. Okay. So what we are going to discuss here in this session is the configuration of a chiral center, right? RS configuration. Okay. So for a molecule to be optically active, right, well, how this particular molecule or a given molecule behave towards plane polarized light, whether it rotates plane polarized light in clockwise direction or anti-clockwise direction, that we can understand once we do the experiment with polarimeter, that when plane polarized light passes through the organic molecule, we can observe the rotation of the light, and we can say that. That's one method. Practical method is that. But obviously in the exam, you're not going to do those that particular experiment, right? Okay. So what we'll do, we have a theoretical method which gives us an idea that whether the given molecule rotates the PPL in clockwise or in anti-clockwise. Okay. So what is that theoretical method that we are going to discuss today? Okay. So a given molecule, you see, heading, all of you write down. All of you write down the heading. It is RS configuration. We have also discussed CIP rule, right? Atomic geometrical isomerism, CIP rule we have discussed, yes? Could you open your notes, all of you? What is CIP rule? Could you open your notes? Yes. Okay. Sequence rule. Yeah, right. So what is that rule? How do we compare the priority of the atoms or molecules? Yes, for isotopes, we have mass number, and for all other elements, we'll see atomic number, right? In case of group, priority or basis of atoms, number of first atom. Yes. So if the groups are there, so the the atomic number of the first atom. So basically, we have to compare atomic number, right? Atomic number. So if you have any group, so what we do to assign RS configuration, write down all of you. We assign, write down, we assign priority. We assign priority we assign priority on the groups or atom attached to on the groups or atom attached to the chiral carbon according to CIP rule, right? Like this. We assign priority on the groups or atom attached to the chiral carbon according to CIP rule. According to CIP rule. So what we have to do, we'll assign priority 1, 2, 3, 4. For example, let's say I am taking this molecule. Okay, suppose we have P, Q, R, S. I am talking about wedge dash representation here. Okay, wedge dash representation. We assign priority on PQRS. Okay, suppose the priority is this. This is 1, this is 2, this is 3, and this one is 4. Now in this wedge dash representation, the condition is what? Write down wedge dash representation. The condition is the least priority group must be into the plane of the paper, away from the observer. Must be away from the observer, means going into the plane along this line. Away from the observer along this line, correct? This is the condition we have. You must have to consider this, okay? If it is not there, then what we'll do, we'll discuss that later. But this is what you have to have, right? the least priority group must be into the plane of the paper, away from the observer. Means along this dotted line that we have. One second. Okay, Shraddha, I'll do that. But guys, one thing you must take care of. When I say something to write it down, you must write it down. Okay, if you do not write, you will be suffering eventually, right? So that's what I said in the beginning. You must have to write down the notes properly. Okay, now you see, I have to repeat it again. Just a second. Okay, those who did not write, we'll see that, Pranav. Just a second. We'll see that. If you all need a break, I'll do that for 10-15 minutes. That's not a big deal. Okay. But let me continue with the session. Okay. Okay. Just a second. Shraddha, write down quickly. First one, the CIP rule. Those who did not write, please write it down. CIP rule, the first point. Higher atomic number have higher priority. Quickly. Higher atomic number have higher priority. Second point, in case of isotopes, we compare the mass number. In case of isotopes, we compare the mass number. Like if you have these isotopes present, for example, write down for the second point, oxygen 18 and oxygen 16. The priority of 18 will be more than 16. Chlorine 37 have more priority than chlorine 35. Okay. Tritium, deuterium, and then hydrogen, protium. This is what we do in case of, isotopes. Third point. When groups are attached to the carbon, we'll assign the priority on the basis of, the atomic number of the first atom. On the basis of the atomic number of the first atom. For example, if you have chlorine attached to the carbon, and then we have SO3H, OH, NH2, all these groups are attached. Then we'll compare the atomic number of chlorine, that is 17. For sulfur, it is 16. For oxygen, it is 8. And for nitrogen, it is 7. Right? So order is this, priority order is this, according to the atomic number of the first atom. Last point. Lone pair is considered to have 0 atomic number. Lone pair is considered to have 0 atomic number, and it will have the least priority always. And this will have the least priority always. Okay, fine. What happened, Pranav? You had class today, physics, right? Who all had class today? Physics, I think HSR and YBR guys, right? Okay, fine. So if you need it, you just let me know after 1 hour. Okay, I can give you a 10 minutes of break on it. Okay, fine. So this is the rules we have. On basis of that, we can assign the priority on these groups attached to the atom. And this is the order, suppose I am getting here, 1, 2, 3, 4. Okay, I will do so many examples, you will understand it. I'm just taking a random example over here to make you understand, correct? So you have this priority 1, 2, 3, 4. Then what you have to do, you have to start from the highest priority, right? You have to start from the highest priority and you have to go till the third highest priority. That is 1 to 3rd you have to travel. Okay, you start from 1 and go to the 3rd priority the group has. Okay, so what I am telling you, that you have to trace this path. Okay, you have to trace from first priority to 3rd priority group. First to 3rd you have to go. And it's not like you can go directly like this. No. First to 3rd you have to go via 2nd always. Right? Means what? From first you have to go to the 2nd priority first. 1 to 2. And then 2 to 3. Right? 1 to 3rd. Directly it is not possible. You won't do this. This is the way we have. 1 to 2 and 2, 3. 1 to 3rd you have to go via 2. Okay. So this, if this path or this trace that you are doing, if this path is, suppose, if this is clockwise, two possibility only we have. Either it is clockwise or anti-clockwise. If it is clockwise, then the configuration is R. If it is anti-clockwise, then the configuration is S. That is what you need to do. Okay, R stands for a Latin word. You don't have to memorize this. I'll just write down here. Not that important. R stands for a Latin word that is rectus. Rectus means right. Right, a Latin word. S stands for, again, a Latin word that is sinister. And this means left. Okay, that's why we use this R and S. So for any molecule, if the molecule is given, you assign priority first, 1, 2, 3, 4, right? And you go from 1 to 3rd via 2. If the rotation is clockwise, then it is R, otherwise it is S. That is what you need to do. Copy this down, we'll do some example on this. Done? Okay. Now, based on this, you see this example. We have carbon CH3, and then we have Br, ClH. Try to find out the configuration of this carbon atom. Is this a chiral carbon? Is it optically active? Is it optically active? Because chirality is defined only for optically active compounds. Okay, so find out the configuration R or S. Is it R? So what we do here, we first assign priority, right? So chlorine, bromine. Bromine has the highest priority 1, then chlorine 2, then this one is 3, and hydrogen is 4. So we already have least priority group. This is second. We already have least priority group on the bottom of this thing, like along it is going into the plane of the paper. Then the condition is satisfied. Then we have to go from 1 to 3rd via 2, right? From 1 to 3rd via 2, like this we have to go. This rotation is clockwise, and hence the configuration for this one is R configuration. Is R configuration. Understood? Easy. Now you see this molecule here. This is Cl. This one you find out the configuration. All 4 you find out. Try all of you. I got your answer, Archit. Done, all of you? Okay. Now you see, if I assign the priority here, I'm doing the second one. This is 1, this is 2, this is 3, and this one is 4. This is 1, 2, 3, and 4. 1, 2, 3, and 4. Okay, just a second. Yeah, hi. Sorry, I got a call actually. So 1, 2, 3, 4 we have. Now you see here, okay. If you see this rotation here from 1 to 3rd, we have to go via 2. So we have to go from here and like this, right? So it is anti-clockwise orientation, and hence the configuration is S here. Okay. Next one you see from 1 to 3rd we have to go, which is this one. From 1 to 3, it is clockwise orientation, and hence it is R configuration. R configuration. If the last one you see, the configuration for the last one is 1, 2 to 3, we have to go like this. So it is anti-clockwise orientation, and it is S. Okay, S. So what happens here? RS we are getting. Now, if I ask you here one thing, that if I want to go from first, suppose if I number this is the first one, this is second, this is third, and this is the fourth molecule we have. Right, so 1 to second if you have to go, 1 to second if you have to go, then what you have to do? What change you will do in the first one so that you will get the second molecule? The change is what? You have to change the position of Br and CS3. So what we can write here? We can exchange Br and CS3. Or we'll write down like this. Interchange the position of Br and CS3, right? Interchange the position of Br and CS3. Correct? You will get this. Now, if you want to form third from the second, third from second, what we have to do? Can you tell me? 2 to third if you want to go, then what we have to do? We have to interchange the position of Cl and Br, and in the last one, we have to interchange the position of Br and CS3, correct? Br and CS3. Okay. So for in all these changes, if you change this, the configuration become R to S. Further you change S to R, and again you change R to S. Correct? So if you observe this, when we have one exchange, means one pair is getting exchanged, Br and CS3, the configuration of R becomes S. Yes, one exchange you see, S becomes R. One exchange, you see, R becomes S. So whenever you have one exchange, don't write this. Whenever you have one exchange, what we are observing here, R becomes S and S becomes R. Correct? Now, if you consider this one, from here to here, 1, 2, 3 to 4, okay? We have one pair of exchange here and one pair of exchange here and another pair of exchange. So if I am considering from 1 to 4, if you have to go directly, from 1 to 4, if you have to go, how many pair of exchange we have? 1, 2, and 3. Yes or no? Tell me. It's very important. 1 to 4, if you have to go, 3 pair are getting exchanged, right? So what we can say here, that if one pair of exchange is there and 3 pair of exchange is there, the configuration changes from R to S. Is it right? Can we say that? One pair of exchange or 3 pair of exchange, then configuration changes from R to S. Okay. So how we can generalize this? We can generalize this whenever we have odd number of exchange, like 1, 3, 5, 7, 9. Whenever we have odd number of, yes, Gayatri, that's right. Whenever we have odd number of exchanges, then R becomes S and S becomes R. Is it clear to all of you? Yes. So write down this note here. Whenever we have odd number of exchanges, we have odd number of exchanges, R becomes S and S becomes R. Odd number of exchanges, configuration changes from R to S or S to R. Clear? Now you see this. If you want to get third from the first one, what we have to do? One pair of exchange and then another pair of exchange. Means 2 pair of exchange the configuration remains same. Yes or no? So how can we generalize this? We can generalize this whenever we have even number of exchange, the configuration does not change. Clear? Whenever we have even number of exchange, the configuration does not change. Write it down. Done, all of you? Okay. So even number of exchange, there is no change in the configuration. Wait a second, Gayatri. We'll do that. Okay. Even number of exchange, there is no change in configuration. Odd number of exchange, the configuration changes. Correct? Okay. Now another thing, sometimes what happens, you will get these 4 molecules in the question, and they'll ask you what is the configuration of these molecules respectively, and they'll give you options like this. They'll give you options like R, S, S, R respectively, R, R, S, S respectively, and so on. They'll give you 2 more options like this. Okay. So in this kind of question, whenever we have same molecular formula, you see all these molecules has same molecular formula, but the relative distance of the atoms or groups are different in the in all the molecules, right? Means the orientation in the space is different, right? Molecular formula is changed, correct? It is same. So you don't have to assign the priority in all 4 molecules and check whether it is clockwise or anti-clockwise, right? You don't have to do that. Now, suppose you haven't assigned this, I'm just assuming this, you haven't assigned all these atoms here, and you haven't done this by this method, RS config that you have done already. What you do, you just pick one molecules, okay, one molecule you pick, and do the same thing that we have done over here. Like you have done for this one, you got it R. Now you start comparing the all other 3 molecules with this molecule and check how many exchange possible, right, to get the other molecules. Like suppose this one you have done, and for this one you can see there's one pair of one exchange we have, means odd exchange. If this one was R, this one should be S. For this one, even exchange, if it is R, this one is R only. If this one is odd exchange, if this one is R, this one is S only. So what I'm telling you, just do this particular method for one single molecule. You don't have to do this for all the 4. For one molecule you do and start comparing with the other molecules given in the question. You can easily get it R or S configuration, right? Did you get it? Tell me, all of you. Yes. Now look at this question here. Suppose we have a question. Carbon with CS3. We have CH2, CH3. Here we have OH. Oh, I'm sorry. We have hydrogen, and here we have OH. Tell me the priority here and configuration of this molecule. Yes, yes, Sresh. That's the same thing you have to do. Okay. Okay, just a second, Archit. Okay, if you assign the priority here, see this. If you assign the priority, what you will get? This is oxygen, then carbon, carbon, and hydrogen. So obviously, the hydrogen has the least priority, that is 4. Okay. Then oxygen, carbon, and carbon. We can compare oxygen and carbon. So oxygen is 1. This is carbon and carbon, so we can't compare here, right? Because both have the same atom. Okay. If in this case, if the case is like this, that first atom is same, then we compare the second atom. Second atom is not hydrogen here. In the primary chain is carbon-carbon bond. So carbon, the second atom is carbon here, but here we do not have any choice. So here we consider the second atom as hydrogen. So carbon, hydrogen, if you compare, carbon has more priority. So this is 2 and this is 3. Okay, just a second, just a second. Okay, so like this, we assign the priority here. And then if you go from 1 to 3, you are getting this as anti-clockwise orientation, and hence it should be R, and that is what you have done, most of you, right? But this thing is not possible because the condition is not fulfilled here. Yeah, right. So condition is what? The least priority group must be in the bottom of the vertical line. Must be in the must be going into the plane along this line, right, at that line. Then what we have to do, then we have the method. What we'll do here, we'll exchange the position of the group which is present here with this line and the group which has the least priority. Means we exchange OH and H. Then what we get here, we have carbon, methyl, and ethyl is as it is. Then we get here H, and we get here OH. And now we can find out the priority of this particular molecule, the configuration of this molecule. It is 1, this is 4, this is 2, and this is 3. So we'll go from 1 to 3 like this via second, and this is anti-clockwise. So this one is R configuration. If this is R, then we'll go back. One pair of exchange gives you this. If it is R, this must be S. Oh, just a second. It is anti-clockwise, so it is S. This one is S anti-clockwise, 1, 2, 3, it is S. And hence this one would be R. Yes, it's other way. So first we'll interchange the atoms or groups to fulfill the condition. Once it is done, we'll find out the configuration of that molecule, and then we'll check how many pair of exchange we have. Accordingly, we'll find out the configuration of the original molecule. Understood, all of you? Okay. So you must remember this, how to do this and the condition here for this molecule. Okay. Now in this one, we have one more thing, that if suppose Fisher projection is given, I think last class we have discussed Fisher projection. If Fisher projection is given, then what we have to do? Fisher projection, if you remember, we have something like this. Okay, suppose we have OH here, we have chlorine here, we have H here, and we have CH3 here. This is Fisher projection, right? We have discussed this, but what do you mean by this actually? This is not a planar molecule. It is not planar. Always keep that in mind. It is not planar. The horizontal line is coming out of the plane. The actual thing, if you draw, this is the carbon atom here. So if this carbon is this, and the horizontal bond that we have, it is coming out of the plane. So it is something like this. So CH3 and OH is this, and the vertical line, it is going into the plane like this. So we have Cl here and we have H here. So this is the actual representation of this Fisher projection. Last class, I think I have discussed this, yes or no? So it looks like planar, but it is not a planar molecule, right? So the condition to assign configuration here, if Fisher projection is given, then the condition is the least priority group must be on the bottom of the vertical line. Vertical line must be on the bottom of it. So write down this note. The condition is the least priority group must be on the bottom of the vertical line. Again, if it is not there, then we have to do that exchange and find out. Okay, same thing we have here, same method. Okay, so could you tell me the configuration of this particular molecule? All of you are getting R? Okay. So if you assign the configuration here, it is 1, 2, 3, 4. List priority already on the bottom of the vertical line. Nothing we have to do. And we go from 1 to 3 via 2. So it is clockwise orientation, and the configuration is R configuration for this. Okay. So this is what we have to do to find out the configuration here. You can have 2 chiral center also in a given molecule, right? So mostly you will get 2 chiral center. I'll give you one example of 2 chiral center also. Look at this example. So suppose we have CS3 on the top, CS3 on the bottom, and we have OH here. We have OH here. Try this one. Tell me, done? Okay, I will check that. Okay, you see this. See, there are two chiral centers here. One is this, and other one is this. Two chiral centers. Okay. So we have to find out the configuration of this carbon and configuration of this carbon. So to find out for this one, the upper one, we'll do that for upper one first. This is 1 because the first atom is oxygen, carbon, hydrogen, and here we have carbon again, right? So this one is obviously 4th, and this one is 1. Any doubt in this? Because if you make mistake, this is the point where you can make mistake. Once you have done the the priority thing properly, then you won't get it wrong, right? So 1 and 4. Now the carbon and carbon you compare, obviously we cannot compare carbon and carbon. Next atom is hydrogen, next atom is again carbon here. So this one is again, it is 2, sorry. So this one is 2 and this one is 3. This is the priority here. This entire group is 2 actually. You see this? This entire group is second group we have, because for this particular carbon we have 4 groups attached: OH, CS3, H, and this the bulky one. Okay, so we have to go from 1 to 3 via 2, correct? So we'll go from 1 to 3 via 2, and this is what, this is clockwise. Is it clockwise? Can we do that? No, we cannot do this. No, we cannot do this. Why? Because the least priority group is not on the bottom of the vertical line, right? So what we'll do, we'll exchange the position of these two. So quickly, if I do this this exchange here, then what we get, you see. So we have this OH here, CS3 here, and hydrogen we have here, and this is carbon with OH, CH3, and H. This is the group we have, second group, right? So now it is 1, 1, 2, 3. So we'll go like this: 1, 2, 3, and 4. So 1, 2, 3 we have to go. So it is clockwise. This is R. So this configuration here, if this is R, then this one would be S. So this configuration is S. Is it clear? One exchange we have. We'll consider the primary chain, Aditya, carbon-carbon. If we cannot do with primary chain, then the substituents will consider. Right, this one is S. Why? Because it is R, so this one is S. Now, if you talk about this one, obviously this is, I'll do this one here. I'll change the color so that you can understand this. This green one. So here it is fourth. For the lower carbon, it is, oh, I'm sorry. This is 4, this is 1, this is third, and this is second. This is second. So we'll do the change here also because fourth is not on the bottom. So change is what we'll consider like this. We have H here, CH3 here, and OH this side. And whatever group we have here, it has the second priority, right? C with CH3, OH and H. So priority is 1, 4, 3, and 2. So 1, 2, 3, if you go like this, it is anti-clockwise. So this one is S. So this configuration is R. Any doubt, Meghna? No? Okay. Did you get it? Yes, yes, yes. They will give you 2 options. Okay, so from this you can easily find out R and S configuration, right? Now there are few terms that we use for optical isomerism. That term you write down here, enantiomers. Yeah, you can do that. Enantiomers. Enantiomers, write down. These are the compounds. These are the stereoisomers, write down. These are the stereoisomers. These are the stereoisomers which are non-superimposable mirror image of each other. Which are non-superimposable mirror image of each other. Are called enantiomers. Non-superimposable mirror image of each other. This compound you see, we have carbon-carbon double bond. Here we have chlorine. Here we have hydrogen, H and chlorine. Carbon-carbon double bond. And when you take the mirror image of this, like this is the mirror suppose we have, then what we get here, you see, carbon, double bond, carbon. This chlorine has a mirror this side, image this side, H this side, chlorine this side, and H this side. Now, if you want to place this carbon, if you want to place this molecule over this molecule, obviously this hydrogen comes over this chlorine. And this hydrogen will, and above this hydrogen, we have this chlorine atom. if you want to place this molecule over this. Because superimposable means what? When one molecule is placed over another molecule, the both molecules looks like similar. Both molecules looks like one single molecule, identical, right? So, oh, I'm sorry, this is a mistake we have. This is hydrogen. So these two molecules are not superimposable, but they are mirror image. So these two are enantiomers of each other. Non-superimposable mirror image are enantiomers. Okay, how do we understand superimposability? You just take this carbon atom, like suppose this is the first carbon, this is second carbon. This is first and second carbon. You place this carbon over first carbon over this carbon, first carbon, second over second. If all atoms are getting superimposed, identical atoms, then the molecule is said to be superimposable, otherwise it is not, right? These two are enantiomers, non-superimposable mirror image. Okay, now what happens, you see, if you take equimolar mixture of these two are enantiomers. Suppose you take 10 moles of this and 10 moles of this and you mix it. So we'll have the equimolar mixture. So that equimolar mixture of enantiomers is called racemic mixture. Yes, ethene is superimposable. You can say that. Ethene is superimposable. This one is not superimposable, right? So write down next point here. If you take equimolar mixture of both compounds, this is not superimposable. How it is superimposable? This is not superimposable. To check whether the molecule is superimposable or not, you place this molecule over this molecule or this molecule over this molecule without flipping it. Flipping is not allowed. Okay, means you can do some changes in the molecule. You can rotate the molecule in the plane, but you cannot flip it. Means you cannot flip the molecule this way and place it over this molecule, right? So always take care of one thing. Whenever you are checking superimposability, flipping of molecule is not allowed. Means you cannot flip this molecule like this and place this over here. Then it comes to be superimposable. So out of the plane rotation is not allowed. Okay, you cannot rotate this molecule this way so that this chlorine comes this side, this hydrogen comes this side. That we cannot do. But yes, we can. This one is not allowed. Okay, this one is not allowed. But what we can do, we can rotate the molecule in the same plane. Means we can rotate the molecule like this. We can rotate like this in the molecule. If you rotate like this in the same plane, like you are, turning the steering of a car, like that. Okay. Are you able to imagine it? The rotation, right? Like if you turn the steering of a car, it's the same thing. In the same plane, you can rotate. This is allowed. Flipping is not allowed. Wait just a second. That's what I'm trying to make you understand. Sometimes what happens when you rotate the molecule like this, it comes out to be superimposable. Right. So you have to check that. But those kind of questions, they won't ask you in KVPY. But I'm just giving you an insight of it. You don't have to take care of all those. Right. This kind of rotation is allowed. You can do this kind of rotation and check the molecule is superimposable or not. For any instant in this rotation, not flipping, I'm talking about rotation. For any instant, at any instant, if the molecule is superimposable, then it is said to be superimposable, and hence they are not, they are not enantiomers of each other. So coming back to the definition, enantiomers are the compounds which are non-superimposable mirror image of each other. Okay. Now the second point is, if we mix the enantiomers, equimolar mixture of enantiomers, if you take, then the mixture that we get is called racemic mixture. Write down the point, racemic mixture. RACEMIC, racemic mixture. Write down, if we take equimolar mixture of of two enantiomers having same molecular formula, having identical molecular formula, having same molecular formula, then the mixture we get is called racemic mixture. Then the mixture we get is called racemic mixture. Racemic mixture, right? Next line. Racemic mixture is optically inactive. Is optically inactive. One note you write down. Just a second, Shreyas. Just a second. Next point, write down. All enantiomers are optically active. Yes, Shreyas, racemization is related to this, but that we discuss in a chemical reaction, not over here. Okay, all enantiomers are optically active. So properties of enantiomers, racemic mixture, you must remember. Okay, you must keep that in mind. Okay, one more term we have that we call it as diastereomers. Write down the next point. Diastereomers. Write down. Write down. These are the stereoisomers. These are the stereoisomers which are not mirror image of each other. These are the stereoisomers which are not mirror image of each other, are called diastereomers. Diastereomers. Like you take this example, cis and trans isomers can never be the mirror image of each other, right? Suppose this example you see carbon, this H and this one. This one is cis or trans? Tell me. This one is cis or trans? This one, the first one. This one is trans and this one is cis, right? These are stereoisomers, geometrical isomers, right? But they are not mirror image. You see both chlorine on the same side, here it is opposite side. So both are not mirror image of each other. Molecular formula is same, right? They have the same molecular formula. So same molecular formula, but they are not mirror image of each other. Same molecular formula, but they are not mirror image of each other, are called diastereomers. So all geometrical isomers, this is very important, write down. All geometrical isomers are diastereomers. diastereomers of each other. All geometrical isomers are diastereomers of each other. Okay, next point. Diastereomers can be of any combination. Diastereomers can be of any combination. Both compounds can be optically active or optically inactive, or one is optically active and other one is optically inactive. All possible combinations we have here. Diastereomers can be of any combination. Both compounds can be optically active, optically inactive, and one optically active, other one optically inactive. Next one, diastereomers have different physical properties. Diastereomers have different physical properties. Have different physical properties, and they can be separated by physical methods. And they can be separated by physical methods like fractional distillation. Like fractional distillation. Okay, so these few properties of diastereomers you must remember. Okay, important. Not much important for KVPY, but you never know what question they are going to ask. So you must keep that in mind. Okay. Now another thing is, if you have a molecules, right? Like if you see this molecule. Okay, I'll give you some examples here. With that only we'll discuss. You see this one. Enantiomers are non-superimposable mirror image, right? Enantiomers are non-superimposable mirror image. So you look at this example. After this, we'll take a break for 10 minutes. Okay, Pranav, fine. Are you there? Yes, we'll have it, we'll discuss it and then we'll take a break for 10 minutes. You see the examples are, we have OH here, COOH on the top, we have CS3 here, and H here. This one is OH, H, COOH, and CS3. We have H, CH3, COOH, and OH. A, B, and C. Okay. You tell me the relation between among this A, B, like A, B, and C. What is the relation between A and B, A and C, and B and C? Or which pair is which pairs in this is enantiomers of each other? Pair of enantiomers, you tell me, A, B, and C. Remember, non-superimposable mirror image. A and B are enantiomers. What about A and C? Are not mirror image, right? So obviously, if you look at this molecule, if you place a mirror here, it looks like the mirror image, right? And they are non-superimposable because if you place this carbon over here, this OH comes over H, H comes over OH. So they are non-superimposable mirror image, right? So A and B are enantiomers, you see. Enantiomeric pair are A and B, okay? Because it looks like. Now you see, whenever you get this question, the best way is what? The best way is to find out the configuration. And we can find out the exact configuration, but I'm telling you to save the time, you don't have to find out the exact configuration here. Suppose randomly I am assuming the configuration of the first molecule is R. You can find out the actual configuration, but I'm assuming this. Let's not waste our time in finding out the configuration of this carbon atom. This won't affect your answer, how you see this. If this is R, then what is the configuration of this one? Could you tell me? By looking at the number of exchange, H and OH is getting exchanged. This must be S. This must be S, yes or no? If this is R, this must be S. And what about for this one? What about for this one? Tell me. This one is S, because if you compare from this one, if you exchange OH and CH3, yes, so fine, not an issue. You can either, Shraddha, you see, this is again I'm explaining. If you take the reference molecule, this, you can take this also as a reference molecule. I'm taking this one. How do you get this one from this? From the first one, from A, how do you get C? By exchange of OH and CH3? Yes or no? So one exchange we have. So if it is R, this must be S. Yes or no? Tell me. Yes. So this two molecule, you see, this two molecule, they have same molecular formula and configuration is also same. It means these two are identical molecule. These two are not different. Only the representation is different, but the molecules are identical. So if A and B are enantiomers, A and C are also enantiomers. What about B and C? B and C are identical compounds. Did you get my point? Are identical. I'll explain this. Wait. This one is R. I am assuming this. I am not giving you the exact configuration. I have just assumed it is R. It may be S also, I do not know. But with respect to this, I am finding out these two. Are you getting it, Shraddha? The actual one, you can assign configuration and find out. Okay. If this is R, this one is S. Any doubt in this? If this is R, this one is S. Any doubt in this? No. If this is R again, how do you get the third one? You exchange the position of CH3 and H. You will get the third one. So if it is R again, this one is also S. So second and third molecules are identical molecules. They have the same configuration with same molecular formula. So if A and B shares the relation, that is enantiomers, so A and C also shares the same relation, that is enantiomers. So enantiomeric pairs are AB and AC, BC are identical molecules. Is it clear? Yes. Okay. Could you tell me the exact configuration of this one? What is the configuration of this one? First one is S. Excuse me. It is 1, it is 2, it is 3, and it is 4. So we'll exchange 3 and 4, 1, 2, and 3. It is anti-clockwise R, so this one is S. Okay. So the correct thing is S, R, and R. So this one is S configuration. This one is R configuration. This one is R configuration. This one is the exact configuration. Correct? This one is exact configuration. But if you get this question to find out the relation, you don't have to waste your time in assigning the priority first and finding out the configuration. I will suggest just assume one random configuration here, R or S, and with respect to that, you can find out this. Yes, A and C are enantiomers because A and B are enantiomers and B is nothing but C. Which one is R? This one. 1, 2, 3. No, it is the fourth group should be here. No, third should be here. So 1, 2, and 3. It is anti-clockwise. R. So the original one is S. It's S only. Clockwise is R. Anti-clockwise is S. Yes. The interchanged one is S. That's why the original one is R. See here, what I did, the interchanged one is R. I'm sorry. 1, 2, 3, and 4. So 3 should be here, 4 should be here actually. So 1, 2, and 3. What is this rotation? This is anti-clockwise, correct? So anti-clockwise is S. Yeah, I'm sorry, it's my bad. S, this should be S and S only. Not an issue. It is R. Original one is R. This one is S. This one is S. Clear? Right, Kinshuk? Correct. So did you get my point, all of you? Yes. So for this kind of question, I would suggest don't waste your time in calculating the configuration of this, to finding out the configuration of this. Just assume one random configuration, and then you can find out by comparing, right? So this kind of question also they ask in the exam, which does not look like appears to be the mirrored image, but still they are enantiomers of each other. Fine, we'll have a break now. Okay, some of you are requesting. We'll start the session at 7:40. 20 minutes left. One small thing I have to discuss more, and then this thing is over. Right? 7:40 will resume. Okay. No, Aditya is correct. You check your things. You check it once, you'll get it. Take a break. 7:40 will resume quickly. Yes. Can you hear me? Shall we start? Aditya, did you get it? Kinshuk, you can watch the recording, you will get it. Okay. So, you see one molecule here. There's one more term that we use. Consider this molecule. Okay, we have suppose CS3 on the top, OH on the right, OH, CS3, H, and H. So if you look at this molecule is optically inactive because of plane of symmetry present into this. Right. So this is a plane of symmetry we have. And we have already discussed when there is a plane of symmetry, molecule can be divided into two equal half, right? And the molecule is not chiral, right? So this is the plane of symmetry, POS, plane of symmetry. Molecule is plane of symmetry, like we have plane of symmetry, hence the molecule is not chiral, and hence it is optically inactive. Optically inactive. This kind of compound where we have plane of symmetry present within the molecule, this kind of compound we call it as meso compound. Meso compound. So what you have to keep in mind that meso compound is always optically inactive. Meso compound is always optically inactive, right? 2-3 terms we have discussed: enantiomers, diastereomers, meso compound, right? Meso compounds are optically inactive. If A and B are enantiomers, then this mixture, the equimolar mixture is racemic mixture, right? This also we have discussed. Equimolar mixture of enantiomers is racemic mixture. So racemic mixture is also optically inactive because we have equimolar mixture of two, um, uh, enantiomers, right? So if this A is optically active, B is also optically active, but the whole mixture, if you take equimole of A and B, that becomes optically inactive. Because suppose if A rotates the light 10-degree clockwise, B rotates 10-degree anti-clockwise. And hence, when eventually the light comes out from this mixture, it is undeviated light. And hence, it is optically inactive. So point is, racemic mixture is also optically inactive. Meso compound is also optically inactive. Okay, understood? Right, these two property you must remember. Now you write down calculation of stereoisomers. How do we calculate number of stereoisomers? We'll use formula into this one. Calculation of stereoisomers. First case, there are a few cases here, 2-3 cases we have. The case 1 you write down. In case of unsymmetrical molecule, in case of unsymmetrical molecule, we have two possibility here. One will get number of optically active form, number of optically active form. This I am assuming as A. And the second one is number of meso compound, number of mesoform, mesoforms. That equals to B. A and B. Sorry, mesoforms M we consider. Number of mesoforms M. So we have two components here, optically active form and number of mesoform which is optically inactive. Okay. So total number of optical isomers, number of optical isomers is equals to number of active form plus number of inactive form. These are the structures we can draw. Okay. So if number of, in case of unsymmetrical molecule, if the number of stereo center, I'll write down here, if the number of stereo center is n, right? Then the number of optically active form that is A is equals to 2 to the power n, because we can have R or S across this, right? Since it is unsymmetrical molecule, right? Since it is unsymmetrical molecule, number of mesoform, that is M equals to 0. I'll give you an example, you will get it. Suppose we have a molecule CH3, okay, CHOH and COOH. Okay, CHOH, COOH. The total isomers here, the total isomers is equals to A plus M, active form and inactive form, and number of stereo center is this 1. So it is 2 to the power 1 plus 0 is equals to 2. Only two molecules possible here, R and S possible. Okay, the name of this compound is lactic acid. Lactic acid. If you see this, in case of this is more important, in case of unsymmetrical molecule, in case of unsymmetrical molecule, first case we have here when n is even. When n is even. So the number of optically active form A is equals to 2 to the power n minus 1. This is what you need to memorize, n minus 1. And M is equals to 2 to the power n by 2 minus 1, if n is even. Okay. In this only, if n is odd, then A value is equals to 2 to the power n minus 1 minus 2 to the power n minus 1 by 2. These formulas you have to memorize. M is equals to 2 to the power n minus 1 divided by 2. Right? So total isomers in the first case, total is equals to 2 to the power n minus 1 plus 2 to the power n by 2 minus 1. This plus this. Here the total will be, and when you add this to this will get cancelled, 2 to the power n minus 1. Okay. Now we'll see some examples based on this. Suppose a molecule is this. We have COOH, CHOH, CHOH, and COOH. Okay, it is a symmetrical molecule. You see around this we have symmetrical molecule. Number of stereo center is 2. These 2 carbons are chiral carbon. So n value is 2 for this one. Symmetrical. I have written here unsymmetrical by mistake. Unsymmetrical we have done the previous one. Let me check this. The previous one was unsymmetrical. Yeah, this one was unsymmetrical. That's why we have taken this unsymmetrical. This one is symmetrical. Symmetrical, this is the molecule we have, correct? Now, so what we do, n value is 2. So when n is even, the formula is this, right? So number of optically active form A is equals to 2 to the power 2 minus 1, that is 2. And the number of optically inactive form is 2 to the power 2 by 2 minus 1, that is 1 minus 1, 0, it is 1. Total number of stereoisomers, 3. In this case, when it is symmetrical. Done. Now, when we see when n value is odd, okay, look at this example. CH2OH, CHOH, 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 and CH2OH. Tell me the number of isomers in this. Done. You're getting 4. So what is the number of stereo center? 1, 2, 3, right? So odd value. So the number of optically active form is equals to 2 to the power n minus 1, that is 3 minus 1, minus 2 to the power 3 minus 1 whole divided by 2. So it is 2 to the power 2, that is 4, minus 2, that is 2 here. Across this we have symmetry. Across this plane we have symmetry. M is equals to 2 to the power 3 minus 1 divided by 2. That is 2 only. So total number of stereoisomers, total is equals to 2 plus 2 is equals to 4 is the answer. One more thing is very important here. If they ask you number of racemic mixture that you get in this compound, number of racemic mixture, tell me. What is the value of racemic mixture we get? How it is 6? You're talking about for this one, Shraddha? Okay. Tell me, what is racemic mixture? Racemic mixture, how do we get? When we mix equal moles of two optically active compounds with same molecular formula. Yes or no? So two optically active form of the same molecule forms one racemic mixture. Yes or no? Tell me, guys. The definition of racemic mixture is it is the equimolar mixture of enantiomers. But the enantiomers, we cannot take the enantiomers of two different molecules, same molecules, right? So equimolar mixture of two optically active forms of the same molecule. Okay, so two molecules you take, you mix the two equal number of moles, you'll get one racemic mixture. So can we say the number of racemic mixture is half of the number of optically active form? Is it right? Number of optically active racemic mixture is half of the number of optically active form, because you see we are getting two optically active form here. So this two, suppose it is A and B, this A and B if you mix, this gives you one racemic mixture. Yes or no? Only one racemic mixture you are getting here. Means two optically active forms gives one racemic mixture. So what is the formula we have? Number of racemic mixture we can write, it is the number of optically active form divided by 2. And this is true for all above 3 cases. Here the number of racemic mixture is 1. In the previous one, no, it is not. Combination is not possible. Suppose you have a compound, any compound you have, and it has two optically active form, A and B. You have another compound, it has also two optically active forms, C and D. So you cannot mix A and C. This won't give you equimolar mixture of A and C, won't give you racemic mixture. Equimolar mixture of B and D won't give you racemic mixture. Both should be of the same compound. Their molecular formula must be same. Then only the equimolar mixture gives you the number of racemic mixture here. Why you want to complex it? Simply, A is the number of optically active form divided by 2. No, you see, if the molecule is optically active, we always have more than one optically active form. Like for example, carbon with HOH, CS3 and Cl. This is optically active. Why can't we draw two different form of it? We can draw it, no, yes. We can draw it, exchange the position. You'll get two, three different form. Okay. What if A is odd? A means fine, not an issue. Any two optically active form you can take. That's not an issue. You can have more than 2, 3, 4 optically active form of a compound. You can have basically 2 at a time to 3C2. We can have 3 optically active form of a compound with one with one stereo center. 3 different forms you may have. So any 2 you can take at a time. Because if you have 3 different form also, the possibility is what? RS or R, 3 different form. Then also the 2 would be same. They are the identical compounds. So you can draw 3 different form, but actually we are having 2 only, 2 different molecules you're having. Because for a given optically active compound, you have only 2 possible configuration, R and S. So no matter whatever number of molecules you draw, we can conclude this to 2 different forms. That is, one is R, other one is S, nothing much. Yes. R and S, see, why it has to combine with R with S only? Because what I said, it's very logical. You see, racemic mixture is optically inactive. Yes or no? Optically inactive. So if you combines R with S, then only they can cancel out. Suppose one is R molecule and other one is S if you combine. And PPL you allowed to pass through this. This rotates this PPL to clockwise. Then since exactly opposite behavior we have in that mixture, this S will also rotate this to anti-clockwise. And finally, when it comes out, it passes through undeviated. And hence the mixture is said to be optically inactive. So opposite behavior is present in that mixture. That is only possible once you take R and S configuration of the same molecule. Clear? Understood? Okay, so this is it for optical isomers. Okay, we have done a lot in this. Okay, but still, if you talk about for JEE, there are few things left. We'll discuss that in the regular classes. But yes, for KVPY, you have a better enough understanding of this. Nothing much more required from this. Okay, few questions if you want, you can solve. You have the book of this thing, KVPY. Isomerism type chapter, you can solve from this. Yes, we always have 2 different forms of an optically active compound. One is R, other one is S. Yes, the PDF book you have, you can solve isomerism question from that. That is what I have taken your question, Gayatri. Probably you did not, focus on that. Suppose you have CS3 here and CS2, CS3. This is what you doubt, right? H and OH. Then, what if there are 2 atoms of the same element or a group? 2 CS3. Then why do you want to decide priority in that case? It is not at all chiral. It is not at all optically active. Not required for this. That is not possible. If 2 CS3 is attached, the carbon is not chiral. We have a plane of symmetry. Molecule is not optically active. If it is not optically active, you don't have to assign priority into that. Yes, tell me. How is symmetrical? We'll have a plane along this. Symmetrical part, I haven't gone through much. We have a plane along this, and these 2 are mirror image of each other. No, not like that. Symmetrical part, we'll let it be. We'll discuss that in IT in regular classes. Okay. Symmetrical thing we'll understand. Here it is not required. So let it be for now. Chirality we'll find out if there is no plane of symmetry, center of symmetry, the molecule is said to be chiral. But symmetry element, I haven't discussed. You just have to focus on the presence of the chiral carbon. If one chiral carbon is there, it is chiral optically active. Symmetrical element we'll discuss in regular classes. It is not required for KVPY. Okay, fine. Okay, guys, thank you. You can solve those those questions, the book given to you, the PDF book. Okay, yeah, take care. And one more thing on learnness, there is a KVPI bundle. Okay, in class 11th, you'll see there is KVPI bundle. In that, you will get the problem solving session or video lectures for KVPI. I have recorded it. There are so many videos there. You can access that also if you want. Okay, you'll get this video also into that. Fine, guys. Thank you. Yeah, take care. Bye.